All right, question 31. It says, which of the following nuclear processes results in an increase in the number of neutrons in the product element? Well, we already went over this in class, and we know that the answers are positron emission and electron capture. Those are the two possibilities where we're going to increase the number of neutrons in the product element. Let me show you why. Okay, if we have a positron emission, let's say we're starting it with element X, we have a mass number of A, we have an atomic number of Z. Okay, if we lose that positron, which I'll represent like this, okay, well, what's happening is we end up with a new element where we still have the same mass number, but the number of protons has dropped by 1. Now, if the mass number doesn't change, that means that the number of neutrons increased by 1 in order to maintain that constant mass. So we have our protons decrease, our atomic number decrease by 1. Therefore, number of neutrons increases by 1. In terms of the electron capture, it's the same rationale, except now we have our same element. And if we capture an electron, okay, what's going to happen to our atomic number then? Our mass number stays the same, but now our atomic number is going to end up dropping by 1. Right? The mass number remains unchanged, and the mass number is the sum of protons and neutrons, which have roughly the same mass. So if the number of protons drops by 1 and my mass number stays the same, that means the number of neutrons increases by 1. So the exact same rationale for number 4. So the answer is 3 and 4. Question 32. The energy equivalent of a mass defect of negative 0.1620 atomic mass units is which one of the following? Well, in order for us to solve this problem, we're going to have to use the mass energy equivalence formula, E equals mc squared. But first, we need to figure out what the mass of this many atomic mass units is in kilograms. How much mass was lost, right? That's what means when we have negative value for our change in mass, right? That's our mass defect. We lost some mass, which is converted into energy. So let's convert that negative 0.1620 atomic mass units into kilograms. And we know that in one atomic mass unit, we have 1.661 times 10 to the negative 24 grams. And we went over atomic mass unit in lecture, so I'm not going to reteach that at this moment. Then we want to convert that into kilograms. You know that there's 1,000 grams in 1 kilogram. You can see that grams cancel and atomic mass units cancel. And now we're left over with our mass in kilograms. And we need the mass in kilograms because we want to end up with units of kilograms times meters squared per second squared, which is the same thing as a joule. So when we work all this spinach out, we get negative 2.690 times 10 to the negative 28 kilograms. Like that, we have 4 sig figs in this number. So when we use our formula, E is equal to mc squared. We're going to use our mass as being negative 2.690 times 10 to the negative 28 kilograms. It's a small mass multiplied by the speed of light, which is 2.998 times 10 to the power of 8 meters per second. All of that squared, that gives you negative 2.421 times 10 to the negative 11 kilograms per meter squared per second squared. And we know that a kilogram times meter squared per second squared is the same thing as a joule. And so our answer is negative 2.421 times 10 to the negative 11 joules, which is C. Question 33. This is a fact that we've talked about several times in the class. We looked at a graph or a plot of nuclear binding energy nuclear binding energy, which was usually measured in mega electron volts, versus number of nucleons, and it had a shape that went something like this. You know, obviously I know there's some discrepancies along the way, but we said the king of the castle was iron 56. Okay, so iron 56 has the highest binding energy per nucleon. So that is just a fact that you need to know. Iron 56 has the highest nuclear binding energy per nucleon. Question number 34, it says, determine how much binding energy is released when thorium-230 decays according to this equation. And it gives us the masses of the thorium, of the helium, and the radium. So the first thing we need to do is determine the mass defect. All right, what's the mass defect here? We're starting out with our mass of thorium, which is 230.033127 atomic mass units. Then when we form these two products, they're going to weigh less, aren't they? Right? They're going to weigh a little bit less because some of that mass is going to get converted into energy. Well, the mass of the one alpha particle, the helium-4, the alpha particle, is 4.002603 atomic mass units, plus the radium-226 is 226.025403 AMU, like that. And then we end up with our mass defect. And our mass defect, and I've already worked out all the math here, is going to be 0.005121 atomic mass units. Now, the amount of mass lost, you can think about it in a negative way. You can think the amount of mass lost is negative, 0.005121, but we'll just leave it as a positive number. You can see that all the amount of energies here are produced or provided rather in positive numbers. And so we're going to use our formula. E is equal to mc squared. But in order to do that, or to use this formula, we have to be able to convert the atomic mass units into kilograms. So I'm going to make it even quicker than I did the last time and say that one atomic mass unit is equal to 1.661 times 10 to the negative 27 kilograms. Our atomic mass units cancel, and we end up with a mass that is 8.5060. And I know I'm carrying an extra sig fig here, times 10 to the negative 30 kilograms. Now we can plug everything into our formula, can't we? E is going to be equal to 8.5060 times 10 to the negative 30 kilograms, multiplied by 2.998 times 10 to the 8 meters per second. All of that is squared. When we do that, we end up with an energy that is equal to, I need a little more space here. What did I write down here? It's equal to 7.655. And I know, again, I'm carrying an extra sig fig here, but I'll round at the end. Times 10 to the negative 13 joules. Now you look at all the answers. These are in kilojoules per mole. This number that we have here, this is in joules per atom, right? That's for one thorium nuclide, okay, undergoing the decay to produce the radium and the alpha particle. So this is per atom. So we know that there are 6.022 times 10 to the power of 23 atoms in 1 mole. So that would cancel out our units of atoms, and that would give us per mole. But now we need to convert the joules into kilojoules. And I know that I have 1,000 joules in 1 kilo, not 1 kilogram, 1 kilojoule, like that. And so my units of joules cancel, and I punch that spinach into my calculator, and I end up with an energy that is equal to 4.61 times 10 to the power of 8 kilojoules per mole. So this is the amount of energy that's released, right? It's released, so I'll give it a positive number. And the answer is closest to A. Okay, here we go. Number 35. If 12% of a certain radioisotope decays in 5.2 years, what's the half-life of this isotope? Now we know that isotopes undergo radioactive decay, which is a first order process. It has a first order, or follows first order kinetics, I should say. And so if we have 12% decayed, that means that I'm going to have 88% remaining after those 5.2 years, 88% remaining. And we know that the amount that's left over after a certain amount of time divided by the initial amount is equal to the negative of the decay constant multiplied by the amount of time. Now we need to have the decay constant in order to calculate the half-life, don't we? Because we know that the half-life, which is what we're looking for, is equal to the ln of 2 divided by the decay constant. Keep in mind that you're going to be provided with this formula and this formula for your exam. Well, let's start by solving for lambda. And we can say that lambda, the decay constant, is equal to, sorry, did I leave my natural logarithm out? I did, there we go. That lambda is equal to the ln of the amount after a certain amount of time divided by the initial amount divided by negative t. So let's punch in some numbers. We get the ln of 88% divided by 100% divided by negative t. The amount of time is 5.2 years. And we end up with our decay constant as being 0.02458 years to the minus 1. I know I'm carrying too many sig figs, but that's neither here nor there to solve the problem. So now I can use my formula for half-life, and I can say that the half-life is equal to the ln of 2 divided by, son of a gun, the natural logarithm of 2 divided by lambda. So I get 0.693 divided by 0.02458. My final answer should only have 2 sig figs. Right? If I have reciprocal years in the denominator, my final answer will be in years. And I ended up with 28.2 years, which is the same, since it's only got 2 sig figs, is 28 years. And so the answer is D, 28 years. Again, you'll be provided with this formula and this formula for your exam. Polonium-208, question 36, is an alpha emitter with a half-life of 2.90 years. So we have a half-life that is 2.90 years. How many milligrams of polonium from an original sample of 2 mgs or 2 milligrams are going to remain after 8 years? So we have the amount of time, and all we were trying to figure out is the ratio of the amount that remains after a certain amount of time divided by the initial amount. And so in order for us to use the formula, the ln of the amount after a certain amount of time divided by the original amount is equal to negative lambda times t. In order to use this formula, we need to have lambda first. Okay, so in order for us to solve for lambda, we're going to use our half-life. So we'll put here, use decay constant to solve for, use half-life to solve for the decay constant. So we know that the half-life is equal to the ln of 2 divided by the decay constant. Therefore, the decay constant is equal to the ln of 2 divided by the half-life. We get the ln of 2 divided by 2.90 years, and we get a decay constant, which is equal to 0.239 years to the minus 1. That is our decay constant. Now we can plug that into this formula, and we can solve for the ratio of NT, the amount after a certain amount of time, divided by the initial amount. I'm going to rearrange this formula to solve for NT over NO, which is going to be equal to E to the power of negative lambda times T, which is going to be equal to E to the power of negative 0.239 years to the minus 1, multiplied by the amount of time, which is 8.00 years. 8.00 years. You see that years cancel, and I end up with a ratio which is 0.148. So this much remains after the 8 years. So if I take my 2.00 milligrams, which is what I started out with, I multiply it by the 0.148, which is a fraction out of 1, or you could call it 14%, whatever, it doesn't matter. I multiply that by 0.148, and I end up with 0.296 milligrams. So that's all that's left over after our certain amount of time, which is D, 0.296 milligrams. Question 37. You've got a rock, and it contains 0.37 milligrams of lead-206 and 0.95 milligrams of uranium-238. Approximately how many uranium-238 atoms were in the rock when it formed billions of years ago? Well, this is a decay that I looked at with you in class, and I told you specifically that you needed to know that 1 mole of uranium-238 undergoes a series of decays to produce 1 mole of lead-206. Okay, so I'm going to rewrite this equation. We've got our uranium-238, okay, and it's going to produce lead-206. If I start with 1 mole of this, let's say, I'm going to end up with 1 mole of lead-206. Okay, the ratio of the decay is 1 to 1. All right, well, in order for me to figure out how many moles, or sorry, atoms of uranium were in the rock to begin with, I need to know the original number of moles of the uranium-238. Okay, so I need, and I'll write it here, need the amount of uranium. Yeah. Okay. Okay. I need to know the original amount of uranium-238. Okay. Well, if at the end, after all the time, billions of years passes by, if I have 0.37 milligrams of lead, that's 0.37 times 10 to the negative 3 grams of lead-206. I know that in 1 mole of that lead-206, I've got what? I've got a mass of 206 grams. So the mass of the lead cancels out, and I end up with 1.80 times 10 to the negative 6 moles of lead. That's what I get at the end, right? That's how many moles of lead I get. How many moles of uranium do I have at the end? Same exercise, 0.95 times 10 to the negative 3 grams, right? I'm just converting this from milligrams into grams. You know that in 1 milligram, there's 1 times 10 to the negative 3 grams, right? That's all I'm using there. So grams of uranium times 1 mole of uranium has a mass of 238 grams of uranium. This cancels, and that gives me the amount of uranium, or the number of moles of uranium. It's 3.99 times 10 to the negative 6 moles of uranium. Well, since the ratio of decay of the uranium to the lead is 1 to 1, that tells me that the total amount of uranium that I started out with is going to be the sum of the 1.80 times 10 to the negative 6 moles of lead, right? Because that came from the decay of the uranium-238, and it was a ratio of 1 to 1. So if I tally up 1.80 times 10 to the negative 6 and 3.99 times 10 to the negative 6, that gives me a total of my uranium as being 5.79 times 10 to the negative 6 moles of uranium. Okay, That's the amount of uranium at T equals 0, right? That I started out with. But that's not what it's asking me for. It's asking me for how many atoms do I have? Well, the last part is simply this. If I have 5.79 times 10 to the negative 6 moles of uranium, I know that in 1 mole of uranium, I've got 6.022 times 10 to the power of 23 atoms of uranium, like that. Moles of uranium cancel, and I end up with a total number of atoms, which is 2 sig figs, 3.5 times 10 to the power of 18 atoms of uranium. Okay, 3.5 times 10 to the power of 18 atoms. So the answer is A. All right, so this question has nothing to do with using a half-life. Even though it's provided for you, you don't need it at all. So it's being able to interpret the problem and seeing what's important and what isn't important. Okay, question 38 says, estimate the age of a bottled wine. It has tritium or hydrogen 3, content that's 60% of that of freshly bottled wine. Tritium decays by beta decay and has a half-life of 12.3 years. So we want to use our formula that the ln of the amount over a certain amount of time divided by the initial amount is equal to the negative of the decay constant multiplied by t, and we want to solve for the age, which is t, right? We want to solve for t. And we can rearrange the formula to solve for t, but in order for us to do that, we must have lambda first. Now I'm going to solve lambda a little faster this time because lambda is equal to the ln of 2 divided by the half-life. So we get the ln of 2 divided by 12.3 years. That gives us a decay constant, which is equal to 5.63 times 10 to the negative 2 years to the minus 1. There's my lambda. And now I can solve for t. So I'm going to say that t is equal to the ln of nt over the initial amount divided by the negative of lambda. Well, how much do I have after a certain amount of time? I have 60%. So that's the ln of 60% divided by the 100% that I started out with divided by the negative of 5.63 times 10 to the negative 2 years to the minus 1. If I have years to the minus 1 in my denominator, then I'm going to end up with years as the unit, and I end up with 9.1 years as being the final answer. And again, I should only have 2 sig figs because I've only got 2 sig figs here. So 9.1 years. Question 39. What fraction of radioactive atoms remains in a sample after 5 half-lives? Well, you could do it like this. You could say, well, I start out with 1, and then after 1 half-life, I end up with 0.5. After a second half-life, I divide it in half again. I end up with 0.25. After a third half-life, I end up with 0.1125. After a fourth half-life, I end up with 0.0625. And then after a fifth half-life, I end up with 0.00. Did I not put 0? Yeah, sorry, that's a mistake in my math there. And I was like, that's not right. So 0.03125. So that's what I end up with at the end, is 0.03125. If you take 1 divided by 32, okay, you get that number. So this is 1 over 32. So you end up with 1/32 in the end. All right. There is a faster way to do that, and that is to use this formula, which is not in our textbook. And that's the amount after a certain amount of time is equal to the original amount multiplied by the half of t divided by the half-life. Or sorry, the number of half-lives. Sorry, my mistake. to the power of the number of half-lives, like that. So we get that the amount after a certain amount of time divided by the original amount is equal to the half to the power of 5. So this is number of half-lives, like that. And you get that 0.5 to the power of 5 is equal to that number, which is equal to 1 over 32, like that. Same thing. Let's see here. And then the last question, question 40, says cobalt-60 is a beta emitter with a half-life of 5.3 years. So T1 half is equal to 5.3 years. Approximately what fraction of cobalt-60 atoms will remain after 26.5 years? So our T is equal to 26.5 years. In order to solve this problem, we need to have our decay constant. The decay constant is equal to the ln of 2 over the half-life. We get the ln of 2 divided by 5.3 years, which gives us 0.131 years to the minus 1 is being equal to our decay constant. Then we can use that the ln of the amount after a certain amount of time divided by the original amount is equal to the negative of the decay constant multiplied by t. We get that the amount after a certain amount of time divided by the initial amount is equal to e to the negative decay constant times t, which is e to the negative 0.131 years to the minus 1, multiplied by 26.5 years. These cancel, and we end up with an amount which is 0.03125, which is the same thing as 1 over 32. I actually ended up with 0.127, but either way, it's close enough. We'll put that it's close enough to 1 over 32, which is answer A.